Okay, so the last lecture of chapter one, we're just gonna wrap up our discussion on resonance, okay? And we kind of covered resonance in the sense that resonance is the distribution of electrons in a pi system, okay? So resonance, from this definition, obviously, we've all kind of now have to agree that you definitely have to have a pi system in order for there to be resonance, right? And we discussed the implication of that resonance structure, in particular with pH, right? So we had discussed the idea that you have um, acetic acid, right? And then you compared that, or we compared it to ethanol, which has an OH as well. And we observed the pKa's of, that should be a capital K. These two are significantly different. 4.8, which would make acetic acid an actual acid, and then ethanol, which is about 16, which however you cut it actually makes it a weaker acid than water. So ethanol is definitely not an acid. And so, uh, and we had discussed, of course, that the acetic acid, the reason this pKa is so much lower is because the electrons here, all right, you have some lone pairs, you have, of course, lone pairs here as well, but one of the things with electrons is, they can move. So you have lone pairs over here, right? And these electrons, because they can participate in a pi system, so if this goes down like that, right? So there's a pi bond here, a pi cloud here. This is obviously a pi cloud because there's got two bonds here. There's a double bond there. So it can actually form a resonance structure by creating a new structure that looks like that. Okay, so we can keep track of these. It's going to be an OH. Right, now you'll notice that if we draw our electrons back on here, here, this, oops, sorry, we've used a pair of electrons actually. Let's be clear. We used the top lone pair here. That was used to generate that bond right there. So that bond, that's now gone, so I can't draw that back. All right, and in that process, actually, these electrons, because that would make a Texas carbon, right? Because then that would make a double bond here, and I've lost that pi bond. Those electrons actually go up here, which means that you now have another lone pair here, right? And three lone pairs on an oxygen actually gives you a formal negative charge. And 1, 2, 3 bonds to oxygen with its lone pair actually give you a formal positive charge. So if you look at it now, right, this electron density, you've actually introduced kind of a formal positive, I mean a negative and a formal positive on both of these charges. That proton can, of course, shuttle, actually. The proton does move. In fact, the proton migrates via a process called quantum tunneling, which is not important for organic chemistry, but if you stick around to physical chemistry, the second semester, you'll learn more about it. But yeah, essentially what you can see is this is a whole pathway unavailable to alcohol, right? There's no pi system here. This is an sp3 hybridizer. It's just sigma bonds. If there were a pi bond, sure, but those electrons are essentially stationary on there. And as a consequence, you have this distribution of electrons that we illustrated as something that looks like an acetic acid, something that looks like this. And with the negative charge sort of being distributed over here, right? There's a negative charge in there, and that's for acetic acid. That's the acetic acid conjugate base. Now the ethanol conjugate base is that. All right, and you know that which one's a stronger acid? by how weak the conjugate base is. And this electron density being smeared over these three atoms makes it more stable than the electron density at this single atom. In fact, if you look at computational modeling that places the electron density only on one atom, what you see is this is ethanol, okay? So ethanol has two carbons, so this is CH3 down here. And the blue part is just like, it's more positive, okay? And that connects to that carbon, which is slightly more negative because of the inductive effect we had talked about. And that goes to this oxygen, which is now minus charge. And you can see there's an inductive effect, right? So if it were all blue, that would be relatively electric. But it's sort of got this gradient where it starts blue, becomes a little green, and then there's like an abrupt change to red, indicating that most of the electron density is super localized here, okay? Now, if we were to do the same sort of analysis, a computational analysis, because these are derived computationally, on acetic acid, what we would see is something that looks like this. Okay, so this is the same sort of pictorial representation of acetic acid, where you have over here, oops, clear that, your H3C, and then that connects to this carbon, and you can see that carbon is actually there's kind of less of a gradation. Like there's more of a gradation where the carbon sort of transitions to that oxygen. And you can see this electron density actually is pretty well distributed over the entire area. And you know, when you share the burden here, it simply becomes more stable. So the electrons are distributed much more across the entirety of those bonds, which means that it is more happy. You know, if we want to attribute human-like emotions to these things, this is a bit happier than this guy, who is not thrilled at being deprotonated. Quite happy to go find a proton, and this one is, you know, quite smiley at the perspective of having lost the proton. Certainly not interested in really reclaiming it. So, as a consequence, you can see that resonance promotes the acidity of this conjugate base is acid, which, as you'll remember, the conjugate base, or the actual acid here is, of course, acetic acid. And the actual acid here is ethanol. Okay, so, and if you really want to be specific with these equilibrium arrows that I've drawn, and remember, these are equilibrium arrows because that goes from a protonated to a deprotonated. If I scroll up, these are resonance arrows because they go between two structures that describe acetic acid. They're two hand-drawn structures that poorly describe acetic acid, to be honest, but they do the best they can. The best illustration, I would say, is this, and even that is the best way to illustrate it. All right, so the equilibrium arrows, we want to be super correct about this, is it would far more favor this one, so that one had to have the larger equilibrium arrow pointing that way. And in contrast, this equilibrium arrow points that way. Okay? Now, as I had alluded to, possibly in the previous lecture, this equal sharing of electrons does not happen all the time. This is a good case where it does happen, but it doesn't happen all the time, okay? This reaction which occurs is an example of unequal distribution where you have an aldehyde, all right, and we had already talked that aldehydes have this partial positive charge or partial negative charge, which means that atoms with lone pairs, like ammonia, they like to attack those negative charges and pop them up there. And this reaction, formaldehyde with ammonia, actually gives you an imine, or this structure that looks like this. So you eventually lose water, and what you end up with is a carbon, two hydrogens, and this peculiar structure, okay, where you have now, and nitrogen is typically quite happy with 3 bonds, but it's got 4 here, which means that it's going to have a formal positive charge, all right? Now this is going to definitely have a resonance structure. So, and the resonance structure would be facilitating nitrogen's interest or nitrogen's journey back to having only 3 bonds and being neutral. And in order to do that, we would draw these paths. And remember that the arrows always represent the flow of electrons, because in organic chemistry, that's really all we care about. And those electrons from the pi bond will go onto the nitrogen atom, which would mean that there's a resonance structure, right? So no chemical reaction has happened. This is just a pushing electrons around on an atom, and you can push two electrons around at the same time. Means that, oops, you have moved the electrons off that carbon, right? So that if you move something away from the carbon, you now give it 6 electrons and an empty pi cloud. And now you've got nitrogen, which is actually okay. And what do those electrons become? Right here, they become the lone pair of nitrogen, all right? So this is a perfectly valid resonance structure, of course. It's problematic in the sense that this particular atom right here is now doesn't have a full octet. You can see up here both of these have full octets. That's a full octet, that's a full octet. They have electrons, they have 8 electrons around them, albeit nitrogen by virtue of its physical nature does not want to share a pair of those electrons, and because it's sharing it now becomes positively charged. Under few examples, with the exception of boron, a full octet is less stable. So that means that actually this resonance structure is more preferred, and it's kind of hard to describe what that looks like. You know, what does an unequal distribution look like in terms of drawing, which is why we're sort of stuck with these crummy electron distributions, right? Because if I show you what an electron distribution for these simple structures, so in computational theory, we can isolate nonsense. We can just say, this structure on the top, what would it be like if it didn't resonate, if those electrons were just sort of stuck in sort of that configuration? And it would look something like this, all right? And that would have like an enormous amount of positive charge on the nitrogen, all right? Oops, let's get rid of that little blip. Let's try that again, because I donked it up. There's an H here and an H here, a carbon, an N and an H here and an H here, right? And the one below it, if I wanted to look at how that would appear, where you have this distribution of electrons, okay, you would end up with something that looks like this. All right, that actually is unexpectedly unequal, mostly because carbon is very angry with you, right? It's got a positive charge, but it doesn't really show it. So it's showing an enormous amount of absence. There's like no electrons. There's your H, there's your H, there's your C, and there's your N, there's your H, and there's your H. So the actual structure is going to have to look more like this one. And if you look at the final structure of these, of what actual resonance, like you just allow the free electrons to minimize, the actual structure looks like this. All right, so you can see the actual resonance structure doesn't look quite, let me just sort of erase this so it can be clear, it doesn't look quite the same as the top one, but it's super, super similar, right? So it's far more like this one up here than it is like the other ones at the bottom. And so in this particular case, even though you can have a resonance structure that is totally valid and a good explanation for the chemistry, it doesn't necessarily mean it's quite right. You're going to have an electron distribution that looks more like this illustration at the top than you are for the illustration at the bottom. All right, so what does that mean practically? Well, if you look at this, it shows you've got a lot of electron density towards the bottom here, which means that in our previous example, we had some sort of atom with a lone pair attack the formaldehyde over here because it was more electron deficient. In this particular case, that's not going to be as favorable. You'd have to have a much stronger reaction to make that go forward, and it would be less slower, okay? Or it would be more slower. So essentially, your reactivity in this particular case would be decreased. Now, for resonance stabilization, you have to remember that we can only push a pair. You can only push 2 electrons at a time. There is something called homolytic bond cleavage, where if you have a pi bond, right, it's perfectly good to push 2 electrons around. That's keeping track of our dots. where we have two lone pairs up here. Now I push that white pi bond up, so now I'm going to put those electrons up here and draw electrons down here, and you'll notice I have taken electrons away from this carbon. It's gone from having 4 bonds to 3 bonds, so now it's got to have a positive charge. It doesn't like that, and as I said, you can actually, let's go from the other side and move this a bit over. You can, of course, you can push the pi bonds wherever you like, as long as you're pushing 2 electrons at a time. You can do something that looks like this. Sorry. Where you just, for whatever reason, choose to push the pi electrons onto the carbon, right? And when you do that, you end up with breaking 1 bond to oxygen, which actually now does not have a full octet. And so it's positively charged. And the carbon, which now has an extra pair of electrons on it, it's still got an octet, but now it's only got 3 bonds, which means it's now got a negative charge. And that, you've broken the octet rule, you put a positive charge on an electronegative atom, that's not, it's valid, okay? It doesn't mean it exists in any meaningful concentration or physical existence, Whereas this, it's kind of broken the octet rule a bit over here on this side, and, 100% of this is like, I guess. I would say that the actual electronic structure is probably somewhere in between these two, right? Where the electron density tends to be more on the oxygen than on the carbon. But one thing you cannot do is there's no homolytic bond cleavage is allowed. You can't just take 1 electron from that pi bond and put it on the oxygen and 1 electron and put it on the carbon, because that is actually a chemical reaction. You are splitting the electron, so it doesn't have a resonance arrow, it has a reaction arrow. And you've put 1 electron on the carbon, which means it now has 7 electrons, which is, that's weird for carbon. And you've put 1 electron on the oxygen, so likewise, nobody's happy in this configuration, all right? You've made a diradical that's now split. So that would be a fairly reactive species if you could do that chemically. But the key take-home for this is 2 electrons must move, okay? And you need to draw your arrow back in, that's the direction, in the direction they move. All right? So draw your, in fact, I'm going to just go over here. Double-head arrow in the direction they move. That's the law, okay? So if you have a formal charge already on a system, so let's say you have acetone, all right? Now acetone, normally deprotonating one of these hydrogens out here, on a CH3, right? We talked about pulling a hydrogen off of a carbon in a couple lectures ago and said like the absurdly high pK of 50. But remember, there is resonance. So if you have a base, okay, and that base still has to be pretty strong, and it has to be a really strong base, but not absurdly strong. You probably do it with sodium hydroxide. You pull that, these electrons come and grab that hydrogen here, and that's a chemical reaction to generate a negatively charged carbon on that side. This negatively charged carbon can now participate in the resonance structure, distributing that negative charge better, which is why you can actually pull that carbon off, or you can pull that proton off, excuse me. So that ends up giving you something that looks like this. All right? And the negative charge is now up here. This is now a pi bond. All right? In fact, I'll just draw that. That's now your double bond, because that's now CH2. You deprotonated one of these H's over here, right? And I've moved it up here. This is actually super stable, this resonance structure. So, which is why this works pretty well. All I've done is I've moved this negative charge to the more electronegative atom, which it's super happy to accommodate, right? And so if you didn't have this resonance structure, this base like sodium hydroxide could never pull off a CH2, right? If this were say just CH3 here, right? That reaction, in the presence of a normal base, if I were to say OH, wouldn't work. There'd just be no way for the electrons of sodium hydroxide to go and pull that off. There's just no, you would end up with something that looked like this, and that is very unhappy to have a negative charge on a carbon with no place to go. All right. You can extend this sort of bouncing around of negative charges, right? So if you want to pretend, and this is why I said, double bonds, just pretend like they're Lewis bases, okay? They're just electrons, right? Because you can just put these electrons here and then here. I move two electrons, I put them to two different structures, all right? So actually, let me stick to my blue arrow convention here. So if I move my pi electrons here, if I move, yes, my pi electrons onto that carbon there, then what I end up with is now I've gotten rid of all my pi bonds because I've now put my electrons directly onto the carbons themselves. But you'll note I have taken, this is still, I'm not drawn it explicitly, but if I show you it's CH2, which means over here, that's still CH2, which means that in these cases, and this is still CH, which means there's still only one H here. So now I've got 3 bonds to those carbons, which means I need to always make sure I have kept my formal charges in place. So this is a valid resonance structure, okay? And it doesn't mean it's actually useful as a thought experiment, all right? It doesn't mean that this is going to contribute significantly in the overall structure. The actual electron distribution of these systems is pretty well distributed, right? So believe it or not, there's these two double bonds can and do talk to each other. But what I've drawn here is not wrong, all right? I started out with a neutral molecule, and this molecule, despite having charges, there's a minus and a positive, that cancels, a minus and a positive, that cancels. So actually this is not a charged molecule either. So I've done nothing wrong, it's just this is not consequential in terms of thinking about how this chemistry is going to work, okay? So as long as you can push electrons around, you can generate valid structures, although doesn't mean you're going to generate a relevant structure, okay? Now, the reason why I can say that this is almost certainly not a relevant structure is, again, I've broken my octet rules here, and I broke an octet rule here. You find the octet rules are really hard to break, and if you break them, you generate typically something unstable, okay? So something to consider is what happens if you have, say, an ether, right? And it's got a leaving group. So we'll discuss leaving groups in a bit, but it's just a group that, we'll call it a leaving group. And leaving groups actually are very happy to be negatively charged. In this hypothetical example, it'll just take its electrons with it and just be like, bye, right? And when that leaving group departs, it leaves behind a positive charge here because it's taken the electrons. And what you have here, and this is why this is a good contrast to the example above it, is a positive charge and that does not satisfy an octet. Now normally, you wouldn't have a leaving group on a straight chain of carbons that would ever do this. But, because just leaving an unfilled octet, that's criminal. But what the oxygen right next to it can do is actually form a pi bond with that to give the electrons to that carbon to make it happy, okay? To satisfy its octet rule. And, the oxygen doesn't actually lose anything from this aside from just some electron density. It's losing electron density, so I guess I should be specific in saying that it does lose electron density, but it doesn't lose its octet, which means that the electrons, now we've actually fixed our octet problem because now everybody has a full octet and this oxygen becomes positively charged. which it's an electronegative atom. It does not want to be positively charged, but it's far better than this scenario where the option is a positively charged carbon that does not have a full octet, right? So in that particular case, you're always better off in trying to stabilize something by filling its orbitals in that row, in that organic chemistry row, the carbon, nitrogen, oxygen, than you are just to leave it empty. And lone pairs are great for filling orbitals. So this actually works pretty well, which allows you to do sometimes chemistry like this next to an oxygen where you have a leaving group. If that were a carbon right here, that would not happen under any circumstances for the most part to have something like that leave. Now, I wanted to drive home one more time. If you've noticed my electron directions, the electrons always flow. The arrows always point in the directions of electron flow, okay? Our last examples have focused mostly on predicting reactivity, and resonance structures are a pretty great way, as I've shown, to do that. They can actually also predict where on a molecule you're going to end up seeing chemistry, okay? So if we just draw this simple system right here, all right, so let's scroll down here, get that out of the way. We know that if you have, or at least we've learned that if you have a nucleophile, because you can imagine this is sort of your aldehyde or whatever you've previously discussed. The electron density sort of focused on this cloud right here. That gives you the nucleophile, these pair of electrons, an opportunity to attack that carbon. And ultimately, if this were, say, an amine or ammonia, that would have given you the imine that we had discussed. What is also interesting and totally predictable through resonance contributions is that it's possible and frequently attack that carbon right there. And you can tell this from the resonance structures pretty straightforward. If you take these electrons, okay, so we're going to, these pi electrons, and put them up here on that oxygen, which as long as we're moving 2 electrons at once and keeping track of our charges, we're totally allowed to do. So we redraw our base structure, oxygen, always keep track of lone pairs, and we see with our blue that they now have a lone pair here because it went up there, and that's going to make it a negative charge because we're down to 3 bonds on oxygen with a full octet. And then the carbon lost a bit of its octet, so now it's got to be positively charged. All right, so at the end it's still negative plus positive. It's still a neutral molecule. We can keep pushing electrons though because we have another pi system here, and that can go down here. We can actually move the pi system over 1 carbon, and that will give us something that, if we keep track of our main scaffolding, the underlying sigma bonds, which you'll note never move, we can move this pi. So this pi system stays white, but the positive charge now is on the end, and the negative charge hasn't moved at all. That's still on the oxygen, okay? So what we see is from these resonance contributors, yeah, we already knew this. We had already talked about this being a part of a resonance contributor. Even though it doesn't have a full octet, you do end up putting negative charge on the electronegative atom, so it's happier. Although, well, it's happier. And that gives us a justification for saying that that's going to be partially positive. Now over here we also have done the same thing. We've really not made much of a difference. All we've done is moved this double bond over, over 1, and that gives us the positive charge there. So this explains why we can have reactions here. It also explains why we will never have this happen, where you have a nucleophile attacking that carbon. That doesn't happen. That there's no way for that to happen. There's no positive charge here, so there would be no reason for something so electron-rich to attack it. And that's actually fairly interesting to think about, right? Because essentially what this structure is saying, if I were to redraw the base sigma framework, all right, that there is a pi system in here that sort of goes like that, all right? And that pi system is distributed amongst these 1, 2, 3, 4 atoms. So the question is, are these all double bonds? Which one are the actual double bonds? And does it matter? Well, it definitely does matter. So double bonds and single bonds have different properties, right? So a difference in double bond and single bond, if you maybe remember from Gen Chem, is the length. So a single bond between 2 carbon atoms is right around, almost without fail, 1.54 angstroms. And a double bond, an isolated lone double bond, not in resonance, not stuck together with any other double bonds where they can do any sort of electron sharing shenaniganery, is going to be 1.32 angstroms, okay? So this is about universally true. If you're going to solve a crystal structure with lots of carbons, these are great values to remember forever and ever, okay? So if we look at a system where we have a distribution of double and single bonds like benzene, right, and a resonance structure where that double bond can move over there, that double bond can move over there, that double bond can move over there, then what we end up with is something that looks like that, or, you know, a pretty realistic painting of benzene really is just having these electrons distributed inside this system in like a ring, right, where it goes around in a ring. That ring is a little bit too small, but you get the gist. That ring just sort of floats around in there. All these are kind of like single bonds, but also double bonds, and that is reflected in the length of each of these bonds. They're the same length, but they don't correspond to either a single or a double bond length. They're 1.39 angstroms, about 1.4, which puts it closer to the double bond length, but it clearly indicates that they share double bond and single bond character, which is an interesting aspect that we will get into, and it has huge implications in reactivity. So that it basically sums up chapter 1. So let's talk about what we did discuss as a component so we can really quickly review, and you can go brush up on things that perhaps you didn't understand or I simply didn't quite explain it to you in particularly well. Part of learning to study is learning that there is not a one-size-fits-all approach to studying. My approach is hopefully helpful for most people. It may not be helpful for you. And if that's the case, then it's important and incumbent on you to seek out that sort of help. And I just drive this home. Listening to the lecture passively is not helpful for almost everybody. And it's not going to be helpful to do super well on this exam. You've got to hit the books, all right? And I would encourage you to come to recitation. You hit the books and you do the practice problems. Recitation is somewhat redundant and unnecessary, but everybody is welcome to come. Now, what we discussed as what we hit on was we first talked about atoms, the nucleus, which we quickly said is not going to be a big part of this course. Organic chemistry tends to focus on the electrons and specifically valence electrons, all right? And there are parts of valence electrons that we started to talk about and the rules associated with valency and the distribution of how electrons are put into orbits, and those are controlled by the Pauli exclusion principle and Hund's rule, two different things that you should really make sure that you're brushed up on. All right, now bonding, we talked about bonds. Specifically, we talked about sigma bonds and pi bonds and how those are two different kinds of covalent bonds, all right? And in those two different kinds of covalent bonds, we have a sharing of electrons, albeit sometimes they're not really equal. In fact, they can be extremely unequal, but they're still shared. That's distinct from ionic bonding, or ionic bonds, which essentially are made of salts. So those are different. There's no sharing. They are attracted by the fact that one is just positively charged and one is negatively charged, a la a magnet, if you will. All right. Then we moved on to how exactly are we going to draw these organic structures. We introduced the Lewis dot structure and really drove home the octet rule so that we would always make sure that carbon always has 4 bonds, carbon always has 4 bonds, carbon always has 4 bonds, carbon always has 4 bonds. I repeated that. There's nothing wrong with your thing, okay? Carbon always has 4 bonds, and never does carbon have 5 bonds, okay? Octet. Don't go over the octet unless you're George C. Olah and you're going to win a Nobel Prize for having discovered a way to do that. And there is a way to do that. Carbon has 4 bonds, okay? Nitrogen typically has 3 bonds. Oxygen typically has 2 bonds. And if you go over those, you introduce a formal charge. And that brings us to polarity. Polarity, of course, from CHEM, you know, is associated with electronegativity, but also you can form formal charges. So if a neutral amine, which is more electronegative than a carbon, that gives you a polarity that would pull your electron density that way. If that amine goes and deprotonates a proton, suddenly that nitrogen is quite positively charged, all right? And that is super polarized towards the nitrogen, okay? So now you've increased the polarity. This also gives us a pretty good foray into acids and bases. Arrhenius definitions you should be familiar with. I would strongly recommend you brush up on how you define pH and how you define pKa and Ka and equilibrium expressions. That is to say, the big K in both pKa and P. And the equilibrium component that defines pH. All right. We had a couple of definitions of acids and bases that were beyond that, including the Bronsted-Lowry, which is helpful in the sense that the base in a Bronsted-Lowry doesn't have to be a hydroxide or a mineral. It can be an organic molecule with 2 lone pairs that can go and attack a proton, because Bronsted-Lowry acids are just protons, whereas we had a Lewis definition in which the Lewis acid was an empty p orbital, right? So it's just a p orbital that should have electrons but doesn't. And some things, like boron and metals, in particular metals, just have empty orbitals to where electrons can go. And these electrons can easily attack those empty orbitals. And that produces conjugate acids for here, and that would produce a conjugate base here. All right, those are definitions you definitely want to keep in mind. Acid strength, pKa. We discussed what dictates acid strength, and that is electronegativity of the conjugate base. So HF, pretty weak acid. HI, great acid. That doesn't have anything to do with electronegativity. That has to do with the sloshiness of the protons in iodide. The bigger atoms tend to make really strong acids. On the other hand, CH4, terrible acid. Whereas HF, comparatively, lots and lots of orders of magnitude better. That has to do with the electronegativity. The bond polarity does help with Lewis acids and Lewis bases through an inductive effect. We did discuss that, but we spent a lot of time discussing how resonance affected pH, the reactivity, and the polarizability. And resonance was a fairly large part of this chapter. Go read your book. Go do your practice problem.